cannot cover the whole proof, but hopefully I will convince you by the end of the talk that there is a lower bound. Please interrupt me anyway if there's something else. Okay, so one of the ultimate goals in proof complexity is to show that there is superpolynomial lower bounds for any propositional proof system. And we know by Cook-Recco theorem that this is equivalent to the statement which says that NP is not equal to CoNP. We know several strong lower bounds for different proofs, big proof systems, such as resolution, cutting planes, constant Frege, and so on. But if we go a little bit higher, we don't know like any lower bound for example, even resolution that works with parities, or like constant Frege that can use parity gates. So why we cannot improve the situation? So apparently there are two problems. The first problem is that we don't know how to prove lower bounds. Like there is a lack of methods. We don't know, like there is no like a universal framework that we can think in it and prove lower bounds. And the other thing, which is also very important, is that like to prove lower bounds, we need a formula. You need a formula, and then you start to try to prove lower bound. We don't have any good candidates. What are the like candidates that we have? Like there are three main candidates. The first one is random formulas, with, for example, like random DNFs with some good densities. The second one is finite consistency formulas. So finite consistency formula says that you have some propositional proof system P, con P of n says that there is no P proof of contradiction of length at most n. And the reason that we believe that like these consistency formulas should be hard is that is because of this theorem by Khaniki and Pudlak. So there is no optimal propositional proof system if and only if for any propositional proof system P, there is another propositional proof system Q such that the finite consistency formulas of Q does not have polysize P proofs. So, and as people believe that this is true, so we get a family of tautologies for any proof system, but I mean, there are some problems with this because like this is non-constructive. So like if I put extended Frege here, we don't know what Q should be, like whether it's Bound arithmetic, ZFC, like something very strong.
Just have to prove, to find out what Q is, you have to prove a lower bound for extended Frege.
Oh yeah.
And then add that as an X.
Yeah, well, there is a cycle there, but so, and the third example, which is the main topic of this talk, is proof complexity generators. So what is a proof complexity generator? So suppose you have some function g that maps n-bit strings to m-bit strings, and m is bigger than n. And it has low complexity. Let's say g can be computed in p-poly. And so as it has low complexity, we can, for any output bit I, we can write a propositional formula like this, in which if you plug some a in p, like this formula is satisfiable if and only if g of a equals to j. And now we can write a propositional formula tau bg for some b here, which says that b is not in the range of g. And we call such a G a hard proof complexity generator for some proof system if for any string outside of its range, like this formula requires long proof.
So it's every string?
Well, I mean, the original conjecture was, the original definition is for every string, but you can say that for almost every string.
Is there anything known about this weak and strong condition of every or just one bit?
Any example that we have is like any lower bound that we know is for every. But for example, if you consider truth table generator, you cannot consider it like for a very strong proof system, assuming like E is not in P poly, for example.
So what are candidate functions for G?
So I will give a okay. So at the origins of proof complexity generators is like there are two like origins. So one was by Aleknovich, and Razborov, Wigderson. So they started with this like fact that PRGs are important in computational complexity. So they asked the following natural question: which mappings should be considered hard from the point of view of proof complexity? Like computational complexity, we can see them as secrets, like proof complexity or like non-deterministic secrets. So that's the question. The second origin was in a work by Krajcek. So he considered like several versions of pigeonhole principle in bounded identity and proof systems, especially this dual weak pigeonhole principle, which we have seen previously, which says that like if you have a polynomial time function which maps like n-bit strings to n+1 strings, there is something which is not in the range. And the question that was he was interested was whether S12 and S12 plus this dual weak pigeonhole principle is the same or not. So we know that like if we put PV here under like some assumptions, these two are different. But for S12, this is completely open. Yes.
I think there's a third paper by Stephen Rudish that's basically asking the same question in more confusing language. Yeah, semi-demi.
Okay. Yeah. Yeah.
Which question?
Sorry.
Which question is repeated in Rudy?
The question of whether like there are random constructions of.
But it's a different question because it's asking about a random B rather than all B's.
That's true.
And that's an important distinction because, for example, if you consider the random CNS correspond to a proof complexity generator, which is proof complexity generator resolution for random B's, but not for all B's. So
okay,
that's a difference.
And okay, and he showed that like if there is a hard proof complexity generator for extended Frege, then these two are different. So we have a sufficient condition. Okay, so here I'm going to explain an example of like candidate proof complexity, hard proof complexity generator. So, and it's Nisan-Wigderson generator. So this is the definition of Nisan-Wigderson generator. We have some base Boolean function f, and we have some matrix A, which is m times n 0, 1 L sparse, which means that each row has exactly L1s and n minus L0s. And Nisan-Wigderson based on f and a define the function from n bits to m bits like this. So the ith bit of the output is you take a, you restrict it to the places that in that row there are ones, you concatenate those bits and you apply f. And that's the function. So is this clear? And let's let me show that. But if f is in NP CoNP, then tau based on Nisan-Wigderson of f and a can be written as a propositional formula. So we can talk about it in proof system. And the main conjecture about these Nisan-Wigderson generators is by Razborov. So he conjectured that any Nisan-Wigderson generator based on suitable matrices and any hard function in NP CoNP, any hard on average function for P poly is hard for extended Frege. That's the statement of standard.
Is there no restriction between some pairwise intersection?
Well, I mean, to have a good Nisan-Wigderson generator, you have to put like the combinatorial properties on the matrix. But like this is the general definition. Okay, so why this conjecture is interesting? So the first reason is that it implies hardness of computation implies hardness of proof. So we have such a relation for weak proof system, which is called physical interpolation property. But when we go to Frege and extended Frege, it fades. And what we know about the status of this conjecture is that like Jan-Pich proved that if P has feasible interpolation property, then Razborov's conjecture holds for P. So, for example, this conjecture holds for resolution or cutting planes if we measure like, size bit of cutting planes. And the strongest evidence that we have to support the conjecture is
I think you should say what it means for the conjecture for P.
yeah, like the same statement, but here we put like another process. And the strongest evidence we have is done by Krajcik. So he showed that like for any like essentially the assumption of the conjecture, he showed that like PV1 cannot prove Nisan-Wigderson generator is not onto. Extending this PV1 to S12 implies the original conjecture. So why a Nisan-Wigderson generator can be hard? So because of the following 4 reasons. So one is the complexity of F. Another one is like the combinatorial properties that matrix A satisfies. So for something, it might be easier to prove lower bound or not.
And if you extend the result in the previous slide for S12, then you get an extended Frege lower bound?
Yeah, at least the way that he did, like Krajcik's, if you somehow can extend Krajcik's construction, you get an extended Frege lower bound. I mean, because you get the conjecture, right? You prove the conjecture. You get a conditional lower bound for extended Frege, if that's what you mean.
So this is automatic, or is
Yeah, this is automatic.
What condition or what condition?
Sorry?
There is a function in NP.
Yeah. If there is a power function in NP CoNP for P poly, when if you prove the conjecture and you assume that the assumption is true, then you get a lower bound for extended Frege. So yeah.
If you assume that the function is hard on average for one of these classes of non-deterministic circuits, do you then get that S12 the theory doesn't prove Nissan-Wigderson is not onto? Like it can give me a part of the function.
If it's NP CoNP, it's already in NP, so you cannot say non-deterministic.
Excuse me, are you saying that if S12 doesn't prove that Nisan-Wigderson generator is
like,
not onto, then you get a lower bound on extended Frege?
Well, almost. That's what I'm
No,
saying.
you get a conditional lower bound.
And because like here you have to start with a model, which is a model of true arithmetic, and the model should be expansion of that. It should satisfy this one.
So you're not saying literally if you replace this one 2 years.
Yeah, like this is like a little bit cheating. For S12, like in S12, you have sharply bounded principle, which means that you can concatenate this falsifying assignment for the Talby formula. So you get like one string which falsifies everything. So here I said that we have to like represent F, because there are several representations. So if F is in NP CoNP, like for any n, we can write 2 propositional formula. One is for the NP part, one is for the CoNP part, which satisfies the natural properties and defines F. And if we have like these sigma 0 and sigma 1, we can write the Talby formula here. And the important thing here is that these QIs are disjoint variables. Now I have to specify what sigma 0 and sigma 1 I want to work with. So I want to give some example. So I'm saying that the parity of some string x equals to 0 can be defined by the following first order formula. So here x is a unary relation, y is a binary relation. And this formula is true, which is this, if you can if y defines a pairing over the ones of x. This is what this formula says. And so this is an example of like first order formula. So if you put the existential quantifier over y, it becomes a sigma 1 formula. And it's not important what sigma 1 formula is, but like this is just an example to what's going on. And we can translate these formulas to propositional formulas. These sigma 1 formulas to propositional formulas. So this is the translation of this formula. We just for every, like if it's xi, we put pi. If it's yij, we put like qij, and then universal quantifiers becomes conjunctions, and existential quantifiers becomes disjunctions. And that's our formula. So here's the definition of what sigma 1 formula is. So again, you have like some first order formula, like the example that we had for the parity. And there are some binary or ternary or whatever relations here. And this formula defines your functions like the way that we had it for parity. And so one important thing is that like these sigma 1 formulas are strong. So you can express any symmetric NP property with them. And another important property of these things is that they are closed under permutations, which means that like, so here in the parity formula, if you start with this, this is your string, and this is your pairing. If I swap these two bits, then you swap the pairing, and you get like again this stain. Like this, the formula still is true for this thing. But this is what I mean by it goes under permutations. So now, like these sigma 1 pi 1 were subset of NP intersect CoNP, so we can define again representation based on them. So the representation becomes like the Paris-Wilkie translation of them. And this is the statement of the theorem for constant depth Frege. So again, we have a function in NP intersect CoNP, but here our function is symmetric and requires exponential size depth to AC0 circuits. Then if we choose like phi 0, phi 1, sigma 1, pi 1 representation of F, and A is a good matrix and B outside of the range, then the tau B formula based on this representation and matrix and F requires line AC0-Frege proofs.
So this is your theorem?
Yeah.
Okay.
What is known about symmetric function hardness? Because
a lot of things should know, but
it seems easy.
Do you even know characterization of symmetric functions?
yeah, I think so.
Sorry, we know.
Do you even know characterization of which symmetric functions are based? It's essentially like the first polynomial.
For AC0, but here it needs to be. Oh, it's AC0, right? Sorry. And
The reason you use this sigma 1 encoding versus like just using the circuits, computing it is to make it bounded depth or
No,
for the symmetry.
and to be able to prove. So that one is completely, it's very hard question. No one knows how to do.
I think why we wasn't at 25.
So I would say there was something about it later. I mean, it's hard to say. I mean, it's hard to explain it right now, but I will say something about it later. Okay. So if the stretch is exponential, you get polynomial lower bound in the size of the formula. If it's the stretch is polynomial, you get exponential lower bound. Okay.
What do you mean by long? You have it in red. So,
yeah,
so you're not looking at the total size, you're looking at the number of lines.
No, like if the stretch is exponential, then you get a lower bound of polynomial size in the both sides of the formula. If the stretch is polynomial, you get exponential size lower bounds inside of the formula. I mean, I didn't want to write both of these, so I could just not.
But it's but it's still
So it depends on the stretch.
So if we say stretch to be like quadratic or something, then it's going to be really exponential. Okay.
Okay. Now, how much time do we have? Hopefully, okay, I can persuade you. Okay, so here, this is the statement of soundness and completeness in propositional logic. So it says that if you have like some propositional formula phi has an extended Frege proof if and only if it's true under every assignment. So this means that if you want to show a lower bound, show that something does not have a proof, you just need to find a falsifying assignment, right? But this thing cannot be used to prove lower bounds for extended Frege, like this kind of a statement, because the formula that we start with is already a tautology. So there is a soundness and completeness for short proofs. So this is a little bit hopefully. So here M is an arbitrary non-standard model of true arithmetic, which means that this is the kind of part. And here we have like some numbers, which is like bigger than everything that we know, but like they are satisfies every properties that we know, like there are infinitely many primes here, like you can talk about graphs and so on. And so here this says that we want to like cut this M, something like this, and put everything which has lengths polynomial in n to the k. Like if you look at the bit representation. And the soundness and completeness theorem says that, so here instead of one formula we should have a family of formulas. It says that this family of formula has a polysize extended Frege proofs if and only if for however you extended this model to a model of PV1, then in that model phi n is a tautology.
Does it have to do something with the how fast growing functions can be proven to be complete in this system? I mean, if you have a fast growing function,
okay,
the question is, can you prove that for every x there is f of x?
Yeah.
So does this have anything to do with the rate of growth that you can prove within the
I don't think so, but if you have a like even if you have like exponentiation, then like you can prove any tautology in an exponential size. So a big function. So is this the statement here? Or semi-clear? But here we want to prove lower one for AC0-Frege, so use this theory, which I'm going to explain here. So this is I delta 0, relativized I delta 0, so it has like basic axioms about addition and multiplication, essentially Q as the previous talk. And we have induction for any bounded formula. And like, so this is an example of bounded formula. Find x. It says that x should be bigger than y, and for any y and z less than x, if the multiplication of these things is x, then one of them should be 1. And but relativized I tilde 0 is essentially the same as I tilde 0, but here your induction formulas can have orbits. Now, this is the only lower bound that I want to show, that to how we can prove lower bounds in this framework. So the statement says that you have a 0 definition of parity, and we want to show that like that this disjunction requires exponential size proof or constant. Okay. So this is the proof. So again, we start with a non-standard model. So what can we do? We want to find a falsifying assignment in a non-standard model, right? This is what we want to do. So we start with a non-standard model of true arithmetic. So we know by the fact that pigeonhole principle requires Planck's proof, like one direction of the soundness and completeness. We can find some function f that like enrich this structure with some function f such that like f is a one-to-one onto from n plus 1 to n, but we still have I delta 0r. And now consider like these two strings. Like without loss of generality, assume n is even. And you have like one, consider these two strings, 1 n plus 1, 0 n, and beta is 1 to the n 0 n plus 1. So phi 1 is true when the number of ones is odd. So we can, like, we know that alpha has odd number of ones, so we can find something here which satisfies this. Again, the same thing for beta and phi 0. But as I said, like these formulas are closed under permutations. So I consider this G, so it maps the n bits by f minus 1. It stretches them and shrinks the second part. So if you have like, this is all ones, this is 0, it's like you somehow map this one to this one in a way that the first part encodes maps to the first part and the second part maps to the second one. So, and if you apply G to the witness to here, you get that, you know, phi 0 alpha G also holds. So this is true, and like so the conjunction is true, which is a falsifying assignment.
Sorry, the first two, the first bullet. So one,
Okay.
mn is a cut.
Yeah, it's an exponential part.
Can you flex the statement of just the last slide? So this is okay. This is not about the generator. I was just
Yeah. Yeah.
Defining the function. Okay. Thanks.
So this is how the lower one was is going to be true for the like tau formula. So there we have a like lot of these equations, and want to like falsify them simultaneously. But we have to choose one x, which is going to be like cut to everyone. So the way that we use x is to we randomly choose 1 and 0, and we apply Chernoff one in a way that like the place that, for example, for parity, here we had like n and n plus 1. So like this is the place that we want to have these many ones and these many zeros. So we choose the probability in such a way that when we get the lower bound, like these things are not too far from the middle. And again, we use pigeonhole principle. But now, so in the parity example, we just needed to like shrink by 1 bit. But here, because like we have, the distance might be more than 1 bit, we need to shrink by more than y bit or stretch by more than 1 bit. So if you have like something that fails pigeonhole principle, you can shrink by more than, like I mean here, this is a function that we can do. So it maps KL to KL minus K. So for each part L, you map it to L minus 1. So there is a K difference. This gives you the lower bound. This was very like intuitive. So there are 2 applications of it. The first one is that you can get a lower bound for random formulas. You choose a random string you choose a random string, and if you choose the matrix randomly, so with high probability, it's unsatisfiable formula, and from the previous theorem, you get the lower bound. And the second application is that you can say some formalization of this statement does not have a polynomial size Frege proof. And the reason is that, so we have like very efficient way of constructing good matrices, design matrices. And like if you fix your F, then you get some kind of special circuits. And these, like the input to the Nisan-Wigderson becomes your advice. So you have like those kind of circuits. I mean, your function does not have those kinds of circuits. Here are the open problems. The first one is to use the like circuit definition of the parity. The second one is, so here, the only functions that I considered was symmetric functions. But suppose you have a binary relation, we can talk about like graph properties. So can you prove the same theorem for that? And the third question is, suppose you enrich your proof system by count modulo P axioms. So can you prove the same theorem when function f is symmetric and hard for AC0?
So any quick question?
Yes.
Yeah, so your assumption was about hardness for depth two circuits.
Yeah.
Is it possible that the NP CoNP symmetric functions are hard for depth two and also hard for P?
And what I wanted to find the minimum assumption, and that was it.
So it's equivalent for symmetric functions. It's equivalent that there's like a point that switches it that's not too close to either endpoint.
Yeah.
So I think it's going to also follow for higher depth.
The last question is there a reason that you didn't put AC0-Frege with mod case?
Then the mod is no any
No, because we have learned Razborov for this. That's why it was
Oh, I
possible.
thought,
Yeah.
like, did you get can you already get a result if you assume F is hard for AC0-mod?
I mean, the argument that I mentioned does not work in this case.
Why? It's not black box like if you have to.
But I mean, here the lower bound that we have is by beam and V's.
Sorry?
There is a PhD lower bound for this system by beam and V's.
I
which
meant
says
if you
that-
had,
Sorry?
like, if you assumed that you had a lower bound for whatever
If you ask what?
if you assumed you had a lower bound for some version of Physical or for some system. I mean, under that assumption.
I mean, here I really use that like it's one bit. I mean, I have hardness for n plus 1 to n. If you have like hardness for n plus 1 to like p to the k to n, then things get a bit messy. At least I couldn't do that. So
It's the opposite. If you have n, something, then it's even harder for the n.
Yeah, so I guess, so let's take further questions offline. It's already a bit late and we'll meet at 2. And so let's take Erfan again.